Hello everyone. In this video, I'm going to talk about Maclaurin series. So let's say we have a function f(x) and we know all the higher derivatives of function at x equal to 0. So here we're going to talk about the point around the point x equals to 0. So then the function can be represented by an infinite power series of the form f(x) is equal to a naught plus a1x plus a2x squared plus a3x cubed, etc. So you can just keep on adding the terms. So this series is called Maclaurin series or for f(x). And what is a naught, a1, a2, a3? So these are all constants whose value depends on f(x), depends on the function. So these are all constants whose value depend on function. And soon you will see how to calculate these constants. So thus the function can be evaluated at any desired value of x by substituting the value of x into each term of the series and summing up the terms. Alright, so next we have, so it can be shown that the series converges to correct value of f(x) as long as the function and its derivatives exist, so they are finite and single valued and are continuous. It means they have no jump throughout the entire interval between x equal to 0 and the value of x where the function is being evaluated. So this is a very strong and necessary condition for the series to converge correctly. So far we learned that the important conditions are that the function needs to be infinitely differentiable and all the derivatives should exist for a correct value of f(x) using the function. So all the derivatives should exist and the function should be continuous. There should be no jumps. So it should be defined in the region near the value x equals to 0. So the function can be approximated by cutting off the series after a finite number of terms, depending on how much accuracy you want. And for the Maclaurin series, the approximation is most accurate near x equal to 0, and it can be made better and better by keeping more terms. So let's consider this function f(x) is equal to 1 minus x. And the Maclaurin series of this function is given by 1 plus x squared plus x cubed plus x4, so on. So this one is very easy to find. So this one you simply do the long division and you can find this series. So you can try if you want. So just use long division and you will be able to find this series. So we notice that the right hand side is of this form, the power series form. And let's try to do few things. So we want to evaluate the function in the neighborhood of 0. So let's evaluate the function at 0.001. So if we use the original function 1 over 1 minus x, so 1 over 1 minus x, and we notice that we get 1 over 0.99. So that is our value. But if we use the series, so which is our this side, right hand side, so also we get this. So if we use all the terms of the series, we get the same value. But if we cut off the series after two terms, so we only use first two, so 1 plus x. So in that case, we notice that we get 1.01. Keeping four terms, we get approximately, so if we keep four terms, so if we keep 1 plus x squared plus x cubed, so we get approximately this. So we notice that so if you try to evaluate the value of function at x equals to 0.01, so it works well. So this series gives us good approximation, so it works well, so no problem from 0 to 0.01. So no problem. Let's try to figure out and try to use this series to evaluate the value of function at x equals to 2. So we notice that if we plug in the value in the left hand side, so we get 1, -1. But if we plug in the value 2 in the right hand side of the series, so we get plus infinity. So series does not converge, but the original function gives us value -1. So what went wrong? Why this didn't work? Any ideas? So the function fx does not satisfy the requirement, remember. So when we talked about it, we said that the function and all its derivatives must exist and be finite on the interval near 0. So we're going to look at interval 0 to 2 inclusive. But here we notice that fx is equal to 1 over 1 minus x, and it does not exist when x equals to 1. So that is the problem. So it does not exist at 1, which is in the interval 0 to 2. So it means we cannot really use this series. So that's why series does not converge. So just remember that the series converges to correct value only if the function and all derivatives exist and there are no jumps throughout the interval between x equal to 0 and the value of x where the function is being evaluated. So don't forget this condition. So now we're going to discuss how can we calculate the constant. So let's say a function fx satisfies all the conditions, so it can be expressed as a Maclaurin series, and that means it can be expressed in the form a0 plus a1x plus a2x squared plus a3x cubed and so on. So in order to find the value of constants a0, a1, a2, a3, etc. So first step is let's try to figure out the value of the function at x equal to 0. And if I put x equal to 0 in our original equation, so this one, number 1, so we notice that we get f0 is equal to a0. So that gives us the value of our first constant a0. So that is simply the height of the function x equal to 0. In order to find the value of a1, so we're going to take the derivative on each side of fx. So when we take the derivative of number 1, so we get f prime x equals to, so derivative of a0 is 0, derivative of a1x is a1, derivative of a2x square is, so a2 as it is, so x square means 2x plus 3a, 3x square plus, so on. So in this case, so what I'm going to do is now we're going to evaluate this at equal to 0. So put x equal to 0, and from here we see that all the other terms become 0 and we get a1 is equal to the value of slope of the function at x equal to 0. So now we're going to find our value of a2. So now we're going to take the second derivative of our fx, our equation 1, and evaluate that x equal to 0. So by taking the second derivative, so we notice that we get second derivative would be, so derivative of a1 is 0, so 2a2 plus 6a3x plus so on. So let's plug in this equal to 0. So putting x equal to 0, we get 2a2. Or in other words, we get a2 is equal to half of second derivative value at 0. And similarly, if you want to find the value of a3, so we're gonna again take the third derivative now and evaluate that at x equal to 0. So third derivative is 6a3 plus 24a4x plus so on. And now we're going to put x equal to 0. So that is 6a3. So from here, the value of a3 is f third derivative of the function at 0, and in the bottom we get 6. So we can write 6 as 3 times 2. Let's try to look for a pattern now. So for we got a naught is equal to the original function, so itself, right? So then we got a1, so the value of the function at first derivative, right, and divided by just 1. Then we got a2, so a2 is the value of second derivative at 0 divided by 2. And then we got a3, so third derivative over 3 times 2. So we can even write this as 2 times 1 here, and we can write 3 times 2 times 1. So this is basically 2 factorial. This is third derivative and 3 factorial. Similarly, I can write this as, so 1 factorial is just 1, and we can write this as, so no derivative, 0 derivative, and 0 factorial. And we see a pattern. So if you have a1, you get first derivative's value at 0, and then over 1 factorial second. Then we have for a2 we have second derivatives value, and then 2 factorial. For a3 we have third derivatives value at x equal to 0 and 3 factorial. So if we have a n, so it means we're gonna have, so a n would be, so nth derivative, its value at 0 over n factorial. So this is how we calculate all the coefficients of our Maclaurin series. Thus, we can write our Maclaurin series in the summation form. So fx can be written as, so in place of a n, so we can write, so as n goes from 0 to infinity, so infinite series, right? So as n goes from 0 to infinity, and in place of a n, we can write the value of nth derivative at 0 over n factorial x raised to power n. So that is our summation form of Maclaurin series. So what does this all mean? So what does all the terms of Maclaurin series tell us? So I'll discuss the geometric interpretation briefly. So let's say we want to estimate the height of a function at some point x, and the only information that we know is about the function that is that at x equal to 0, the height is a naught. So if we only know this one piece of information, that at x equal to 0, the height of the function is a naught, so then we can guess that the function is y fx is equal to a naught, right? So that is our horizontal line. So we can approximate the function using a horizontal line. But if we know some additional information like the slope of the function at x equal to 0 equals to a1, so now using these two pieces of information, so that at x equal to 0 the height is a naught, and also the slope is a1, so the best we can do is we can assume that the slope stays relatively constant and guess that the function is a straight line, and the desired function is given by this equation a naught plus a1 x. So we get to this point. So similarly, if we keep on receiving additional information about the function, about the second derivative at x equal to 0, we can have another term in our polynomial, and we can approximate the function better and better. So if we keep the first three terms, so if we know some additional information about second derivative, then we can estimate our function using a parabola instead of a line only, and so on. So keeping only one term approximates a function using a horizontal line. Keeping two terms, we get a straight line. Keeping three terms, we get a parabola. And keeping more and more terms, we hug the original function more and more, and we get a better approximation. So this is what the geometrical interpretation of our estimation is all about. So a Maclaurin series is trying to approximate the function with the best polynomial possible. Alright, so we got the idea that a Maclaurin series is trying to approximate the function with the best polynomial possible. But what if we already have a polynomial to start with? So we get the result that the Maclaurin series of a polynomial is that polynomial itself, because we have a polynomial to start with. All right, so now we're going to do a few examples and in which we're going to try to find the Maclaurin series for some functions. All right, so in the first example, we need to find the first 5 terms of Maclaurin series for the function fx is equal to 3 times e raised to power 2x. Since we know that our Maclaurin series of this form, the infinite power series form, and we also found that so the constants are found using nth derivative at 0 over n factorial. So this is our summation form of Maclaurin series. When n equal to 0, the function is just the original function, and the value of that at 0 would be 3 e raised to power 2 times 0, which is just 3, and a naught is equal to value of first derivative at 0, so just 3 over n factorial, so over 0 factorial, so which is only 3. Value of 0 factorial is 1. So next, when n equals to 1, it means we're going to find the first derivative. So first derivative of this would be 6 e raised to power 2x. And now the value of that derivative at 0 should be just 6. And a1 would be 6 over 1 factorial, so which is 6. I don't know what is wrong with my one note, but let's just keep going. So when n equals to 2, so second derivative is 12 e raised to power 2x. And then plug in, so evaluate this at 0, so that becomes 12. And a2 should be 12 over 2 factorial, which is, our derivative is 24 e raised to power 2x. And then we're going to evaluate this value at e raised to power 0. So we get 24, and a3 is 24 over 3 factorial, so 24 over 6, which is just 4. And coefficient for our fifth term will be n equal to 4. So fourth derivative is 48 e raised to power 2x. And then we evaluate the value at 0. So that is 48. So 48 over 4 factorial. So 48 over 4 times 3 times 2 times 1. So which is 24. So that is just 2. So a4 is 2. By using these coefficients in our Maclaurin series, we get, so fx is equal to, so it means 3 e raised to power 2x is approximately equals to, so a naught, which is 3, a1 6x, a2 6, x squared, a3 4x cubed, a4, so that is 2x4, and so on. But we just want you to find first 5 terms, so let's just write first 5 terms. So these are first 5 terms of our Maclaurin series. So remember, Maclaurin series is a polynomial that we approximate near x equal to 0. So if you want to find an approximation of this function at 0.5 using the series, so what we can do is, so we will say that, so f of 0.5 equals to, so 3 e raised to power, so 2 raised to power 0.5. So that is approximately equal to, so using the series, it should be 3 plus 6 times 0.5 plus 6 times 0.5 square plus 4.5 cube and plus 2.5 raised to power 4. And the exact value using the calculator, if we found this one, so that is 8.154854854. But since the approximated value is we find using this series, so that is 8125. So these are only 5 terms, so that's why we get approximate value. But if you use more terms, you can get more accuracy. All right, so now what if you want to find it using, so find it for f equals to 2.6. So in that case, I can tell you it wouldn't give us a good approximation because the series is only around x equal to 0. So as you go more and more away from 0, so you won't get the accurate of the values. So I can tell you that if we use this one for our 2.6 value, so there is a huge difference in both values using the calculator. So check the huge difference, check the difference. So I would suggest, so you will see that there is a big difference. I hope that makes sense. So my OneNote is giving me some problems, so I'll do the Maclaurin series for sin x in the next video. Thanks for watching this video.